Hello, dear students. I welcome you again in this lecture series on modern physics. In our last lecture, we talked about Maxwell's equations, their symmetry properties, and then we also derived the equation for the propagation of electromagnetic wave in vacuum. What was most interesting result in our last lecture is that the speed of the electromagnetic waves comes in terms of the fundamental constants of vacuum, the permittivity and permeability. And this result tells us that this speed does not depend on any observer. There is no relative speed to the light. Doesn't matter how you move in you will always find the same speed of light. So speed of light is not relative. That was the main idea we discussed in the last lecture. We also worked on these beautiful symmetries. We saw that the Maxwell's equations retain the symmetry under time reversal. So that means if I reverse time, the form of the equations does not change. Also, the Maxwell's equations respect reflection symmetry. If you change your coordinates from, say, x to minus x, y to minus y, z to minus z, what we call as parity operation, the form of the equations remain the same. We also saw that the equations are symmetric under charge conjugation. That means you replace positive charges with negative charges, the form of the equations will not change. Today we will talk about the energy conservation theorem. It's famously called as Poynting theorem. We'll say that if we have an electromagnetic field, it has an energy in it, and that energy, the rule that this energy obeys, the conservation rule that this energy obeys, so that we have to focus on today. And so it's famously called actually Poynting theorem. So it is like we talked in our earlier lectures, conservation of charge, that you have charge somewhere, and if it is going out, then there is the equation of continuity that tells us that the charge drop at some place is equal to the charge flowing out. And we expressed that in a beautiful equation of continuity, that del dou rho by dou t plus del dot j equal to 0. We'll start from that conservation of charge principle. We'll revise that, and because that would help us in building the conservation of energy. So let's start. Let's start doing that. So let me revise what we did in conservation of charge. You see, we begin with this idea that if you have a region of space, right, you have a region of space, then this region has some charge density in it. There are charges in this region, rho, defined by that rho charge density, and some charges are leaking out. If the charges are going out, then the rate at which the charge is decreasing is equal to the flux of the current that is going out. And this is expressed in terms of the equation of continuity. And how do we write it mathematically? And we write that the rate at which the charge density changes is equal to the flux of the current that is flowing through the surface surrounding this charge, right? Del dot J is divergence of the current density. Or I can put it this way, del rho by del T plus del dot J is equal to 0. This also is called as local conservation of charge. So it says that you start with some charges in some region, right? Some initial charges. Say there were charges in this region, some initial charges. Now these charges would remain there. You cannot destroy them. The fact that the charges are moving out of this region, they are moving out, then the result of that is that the charge density in this region will decrease, right? Now if I play a trick here, if I suppose that there is some source that feeds the charges in the system, suppose I connect something to this region, that the charges are coming into the system or charges are being taken away from the system, and that source is S, then how would I modify this equation of continuity? So if there are sources and sinks within that region, then this equation would modify as del rho by del T plus del dot J is equal to S. Now, if S is positive, it would mean that we are feeding charges into the system, and negative would mean that we are taking charges from the system. So charge can flow, that's fine. It will result in the drop in charge density. But if there is a source within that can where charge is supplied, then that is to be then that would change the equation of continuity. And right, so we have this initial rho was initial charge density. If it is changing with time, it's changing because the charge is flowing out. But at the same time, if there is a source within, that source term would be the S. That S will take care of if there is a source in that region which is feeding charges, or there is sink that is taking charges away. Then this equation would modify like del rho by del T plus del dot J is equal to S. Right? This you must keep in mind when we as will talk about the equation for the conservation of energy. Now let's look into the equation for the conservation of energy for an electromagnetic field. Now this is going to get very interesting. So now you see, how do I start? I will try to bridge the ideas in bits and pieces. Now you know that in high school days, if you have a capacitor, it has two plates, positive and negative. Then inside these plates, between the capacitor plates, and you have an electric field E. And this capacitor is a device that stores the charge, and it stores the energy in the form of electric field E. So this electric field E between the plates contains energy. Right, and that energy is in the form of this electric field. And in fact, you can calculate the energy density of a capacitor. It turns out that the electric energy stored in the field itself for a capacitor is 1 by 2 epsilon naught E square. Right, very nice. And this is when you have a charge, when you have a capacitor which you have charged, say fully charged capacitor, and an electric field E has been established between the plates, then there would be energy in the form of electric field, and that energy density would be equal to 1 by 2 epsilon naught E square. It's a high school stuff you normally derive it in high school. Then we have another interesting device we call a solenoid. And if we pass steady current through the solenoid, say current I is passed through the solenoid, a magnetic field is established, and the energy stored in the solenoid is in the form of magnetic field. And that energy, magnetic energy density for solenoid, is equal to B square by twice mu naught, where mu naught is permeability of this free space. Right, so this is the energy stored in electric field, which is electrostatic field in this case, and this is the energy stored in magnetic field, and here it is the magnetic energy density provided you have steady currents. Right now nothing is moving, right? The magnetic field is also static and the electric field is also static. Static electric field is created by static charges. A static magnetic field is created by steady currents. So far so good. Now we punch. So we now take a region, right? Now I take a region in space. So suppose I have this region of space, and there is electric field and magnetic field in this region. And that electric field and magnetic field could be due to charge and currents somewhere. There are currents and charges somewhere, and because of that, there is the field in this region. Now, in this region, what is the energy stored in the electromagnetic field? Very simple question. So you will ask the question, what is the energy stored in electromagnetic field? What is energy stored in electromagnetic field? Fine. Very simple question I ask you. So I have a region where I have electric field and magnetic field. How much is the energy in these fields? Now you will say, yeah, I can talk about energy density, and the energy density would be U electromagnetic, right? And that U electromagnetic would be 1 by 2 epsilon naught E square plus B square divided by twice mu naught. So quickly you will say this thing, right? This is the energy density of an electromagnetic field. I have electric field, I have magnetic field, and the energy density contained in that field is 1 by 2 epsilon naught E square plus 1 by 2 epsilon plus 1 by 2 mu naught b squared. This one, right? Now, fine so far. Now, if these electromagnetic fields are oscillating, if they are changing in time, then what's going to happen? We have seen that when electromagnetic fields oscillate, they generate electromagnetic waves, right? A changing electric field generates a changing magnetic field. A changing magnetic field generates a changing electric field. So the fact that the electromagnetic field is oscillating, is dynamical, it will create electromagnetic waves, and those waves would travel in free space, right? So this energy would be carried out. So we have to see the relation between the energy that we originally have and the energy that is carried out by the electromagnetic wave, right? So we have to look for that. And then once this electromagnetic wave is propagating, now the electromagnetic wave is propagating, it can see a conductor somewhere, and it can hit the conductor and start oscillating the electrons. So it will feed the energy to the matter. Now, that energy which it will feed, it may be used in heating the element. It may be used in establishing the induced currents in the material. So therefore, this part of energy will go there. Or if you have this electromagnetic wave hitting a plasma, it may generate energy, right? So it could be a generator of energy. So once we connect the electromagnetic waves to matter, so we have a sink term or a source term. Sink, if it's hitting a metal, for example, we could have a generation of energy if it hits plasma under certain interesting conditions, right? So the fact now is that I would like to have the equation of continuity for the energy, where I take care of the initial energy of electromagnetic waves and the electromagnetic field, and the electromagnetic field is dynamical, the energy is carried out in the form of electromagnetic waves, and then if it hits a metal surface, it may actually feed some energy to the material as well, right? So we need to write an equation of continuity which contains all these three terms. So let's now proceed. Suppose I have a charge q, right? And I placed it in an electromagnetic field, E and B. It will experience a force. So naturally, that electromagnetic field will pump energy into this charge. So we'll try to see how much power is delivered to this charge. So the force that the charge experiences in electromagnetic field is given by the Lorentz force rule, which is F is equal to Q E plus V cross B. This is called Lorentz force. It's a force experienced by a charge placed in electromagnetic field, electric field and magnetic field together. Now I want to see how much power is delivered to the charge. For that, what I do is that, you know how to calculate power from force is to take dot product with the velocity. So that would give me Q V dot E plus V dot V cross B. So what I am doing is nothing but taking dot product with the velocity on either side. Dot product of force with the velocity will give you the power delivered to the charge, and just you multiply with the velocity on the right hand side as well. So here is E, the dot product of E with V, and here is V cross B, and I will take dot product with V. Very simple. Now you will recall from the vector identity that it is A dot A cross B if you have three vectors. So this term is anyway zero. This term is zero. It is zero because two vectors are identical. This is the property of the scalar triple product, right? So therefore this term is zero, which also means that magnetic force does not do any work on a moving charge. So magnetic force will not do any work. It's the only electric force that does work. So therefore this term is zero. So we are only left with this term. So how much is power delivered? So F dot V is equal to Q V E. Because when you have a positive charge, when you leave it in an electric field, it will always move in the direction of electric field. So the angle between V and E will be zero if we start from a charged particle at rest, right? So I take it in a very simple way, it is just QVE. So that's what is the power delivered to a point charge. Now, instead of point charge, if you have a bunch of charges, so if you have a bunch of charges defined by their charge density rho, how much power would be delivered to that if placed in the electromagnetic field? So how much power would be delivered to this charge distribution if I placed in an electromagnetic field? All you have to do is to write this Q in terms of charge density. So I write that power P delivered to this system of charges, or a material or a conductor which has lots of free charges, would be equal to integral for Q. I will write the density V E d tau. So this d tau is the small volume, rho is the density, small charge is rho d tau, the entire charge is the integral of rho d tau. So this, for this Q, you are basically replacing it with rho and d tau. That's your Q actually. Rho into volume is your Q. So it is the same thing, Q, V, and E. There is no magic there. Simply, I'm writing the same equation. Now, what do you recognize here? What do you recognize here? You recognize that rho V is equal to J. Rho V is equal to J. It would be equal to current density. That you can justify. Right? Rho V is equal to J. So that is the current density. Now just telling you how that is current density, just to justifying that it is current density is very simple. Rho is charged by volume, and right, so I'll tell you how to do it. Rho is charged by volume, so it is charged by volume. Fine, good. And velocity is some length by time, right? Now rho, sorry, so I'm looking for this term rho into V. So rho V is equal to, so charge by volume is charged by area into length by time. This length and length will go. Charge by time is your current, divide by area, that is your current density. So dimensionally and its current density. So we understand this represents the magnitude of current density. But current density is actually a vector, and so is electric field a vector. Therefore, I can write power that is delivered to the bunch of charges in electromagnetic field is J is a vector. For E is also a vector. I write E dot J because the integrand has to be a scalar into d tau. So this gives me that how much power is delivered to a bunch of charges when placed in electromagnetic field, right? So this gives me the idea of how much power is being delivered to the bunch of charges. Now, but what is my goal? My goal is, my aim is to find out that conservation of charge rule, find the equation of the continuity for electromagnetic energy, right? So there is an electromagnetic energy in the electromagnetic field, and what is the equation of continuity for that electromagnetic energy? That's what I am looking for, right? So I have to write down, discover that equation. And for that, what I did, I talked about initially about the conservation of charge, and showed what kind of equation does it obey, to give an idea what kind of equation I am expecting. And now I just took a bunch of charges, and if I place them in electromagnetic field, how much power I deliver is J dot E. That is power per unit volume, right? The integral of J dot E is the power that you deliver to the charge that is contained in some region, right? So this much is, I think, clear. So we started with that we have an electric field and a magnetic field called electromagnetic field. Then that electromagnetic field has energy in terms of its energy density. And then if there are charges anywhere, then this electromagnetic energy, this electromagnetic field can supply energy to those particles. It can do work on them. It can actually push power in them, right? So it can deliver power in them, and that power, how much is delivered per unit volume, is J dot E. So it is power delivered per unit volume is J dot E, that represents power delivered per unit volume. Power delivered per unit volume to the bunch of charges. So far, so good. Fine. Now, let's look at Maxwell's equations. Let's start with Maxwell's equations now. Now I have these four equations, but for me, I will just take two equations which are important for this kind of derivation. So I have this equation about the curl of E. That's equal to minus del B by del T. This is my one equation. The second equation. And there's a fourth equation, del cross B is equal to mu naught J plus mu naught epsilon naught del E by del T. See, I am looking for E dot J term. Keep that in mind, because that will give me how much power is delivered to the bunch of charges if some charges are in that field. So in order to find E dot J, see, in your mind you have this J dot E thing. That is energy that is delivered to the matter, right? So in order to find E dot J, I will take the dot product with J, all the three terms, right? Because I'm looking for E dot J. So let me do that. So take the dot product with E. So E dot del cross B is equal to mu naught E dot J plus mu naught epsilon naught E dot del E by del T. Fine. So what I have done, nothing, just take dot product with E, dot product with E, dot product with E. Is that clear? Very nice, very nice. Now I want E dot J. So I will divide with mu naught. Mu naught here, mu naught here, mu naught here. This mu naught will go, mu naught will go, and a mu naught will remain here. So the next is to divide with mu naught. So once you divide with mu naught, you have E dot del cross B divided by mu naught. Now I have this E dot J term plus mu naught epsilon naught. No, one mu naught is gone, so this mu naught is gone because I have divided it with mu naught. This mu naught will go. This mu naught will go because you are dividing with mu naught, right? So it is epsilon naught E dot del E by del T. So far, so nice. Now you recognize that this term, I can put it in a very simple form, and I can write it as E dot del cross B divided by mu naught equal to E dot J plus, I can write this as del by del T of 1 by 2 epsilon naught E square. Now you look here, this is very interesting. If I differentiate this, what do I get? I will get 1 by 2 as it is epsilon naught 2 times E del E by del T. This 2 and 2 will cancel, so what do I get? Epsilon naught E del E by del T. That's this term. Because any E dot E, they are in the same direction, so there's no problem. So that's what I get. Fine. So that means that I can write this in terms of this thing, right? I can write E dot del E by del T as del by del T of 1 by 2 epsilon naught E square, right? And this reminds you of something interesting. This is what? This is your electric energy density. It is the energy density of the electric field. So this much is how much? This is energy density of electric field. So I have energy density of electric field, right? Because that tells us that how much power is delivered to the bunch of charges. And we have this E dot J is here, but we have also this energy in the electric field, the energy density 1 by 2 epsilon naught E square. But what we don't have is the magnetic energy density, because if I have electric energy density, magnetic energy density, and then I have something called the source term, so I will have to only look for how much energy is flowing out, right? So that these pieces put together, they will I will get the equation of continuity. So I have to focus here on what I am looking for. So I have this energy density, electric energy density. I have this E dot J term. So that was the focus here, to get that E dot J term. But what's not, what I don't have is magnetic energy density. But if you look at this equation, I can get magnetic energy density from there, right? I can get from this equation, if I take dot product with B on both sides, I can get that magnetic energy density. So I will try to obtain the magnetic energy density from this equation, and I label this equation as some equation 1 or A, whatever you call it. Let's label this as equation 1. Very important equation. Keep that equation in mind. I will refer to this equation again. So now take the equation second of Maxwell's equation and try to calculate the magnetic energy density. So my second equation is del cross E is equal to minus del B by del T. If I take dot product with B on both sides, what do I get? Minus B dot del B by del T. And if I divide by mu naught, I will be able to put in that term. So now this right hand side I can write as del by del T of B square by twice mu naught, because if you differentiate that, you will get this term back, right? So now I am able to convert equation 2 in the form that I need. I have now the magnetic energy density in the equation. Good. And I label this as equation 2. This will be required. Now, my problem is that I have, you can see this. This is very interesting. I have electric energy density. I have the power that is delivered to the bunch of charges. I have magnetic energy density. So I want to put this here. I want to couple these two equations. But you see, on this side, I have B dot del cross E by mu naught. And on this side, I have E dot del cross B by mu naught. They are not same. They are different. So I need to couple these two equations through some rule, so that I use this result in this equation. But the problem is that this side and this side are different. How would I couple electric and magnetic fields? For that, what I do is that I use a vector identity to couple these two equations. In order to couple these two equations, I will use vector identity. So I will use a vector identity. So I need to couple 1 and 2. That's my job. I want to couple these two equations. So what I do is that I will look for a vector identity that may solve my problem. So I will take this vector identity, del dot E cross B is equal to B dot del cross E minus E dot del cross B, right? Now you see that if I divide by mu naught, now I have this term, I have also this term. This term, where is this term? E dot del cross B, that E dot del cross B is here. That's equation number 1. And where is this term? B dot del cross E, it was just found, right? It is here. Divided by mu naught, equation number 2. If you write equation number 2, what is that? B dot del cross E divided by mu naught. So this is your second and this is your first. So you use second and first and plug them here. So you substitute second and first in this equation. All you have to do is just substitute these two equations and you have coupled the two equations. So del dot, come on, E cross B divided by mu naught is equal to, come on, B, for B dot del cross E, come on, use its value, B dot del cross E, where is that? B, it's here only, so it is minus del by del T of B square by 2 mu naught. So we are done with this equation. Now we want to substitute this one, and for that we have, it's a minus term here, right? I will write minus first, Then I have it is E dot J, right? So it is E dot J, right? E dot J, and E dot J. Then what is the next term? Sorry, it was E dot J. Remember? Do you remember? It was E dot J, and there was this plus del by del T of 1 by 2 epsilon naught E square. I think these were the two terms. Let us go back. Let us go back. Yeah, these were the two terms. You can see that, these two terms. Right, so good. So we are here now. Beautiful, we are here. Fine. Now we have this long equation. Now what we do is that we'll put this and this on this side. So all you have to do is that you write del by del t. So we're done almost del by del t. What we'll write, we'll put them together, put them together. It is 1 by 2 epsilon naught e square plus b square divided by twice mu naught plus this term del dot e cross b divided by mu naught is equal to minus E dot J. And we propose S to be called Poynting vector, that is equal to E dot E cross B divided by mu naught, because it points in the direction of the propagation of electromagnetic field. And it is perpendicular to both E and B. It is perpendicular to both E and B. And we call it as Poynting vector. Poynting vector. Right. So this S we introduce as Poynting vector as E cross B by mu naught. And now rewrite down this equation. Del by del T. This I write U electromagnetic, the electromagnetic energy density, plus del dot S, the divergence of the Poynting vector, is equal to minus E dot J. And now you try to recognize these terms. Recognize these terms. This was my energy in electromagnetic field, and if it changes, if that changes, if that electromagnetic field is dynamical, then there is a flow of energy. The S represents how much energy is flowing out, and then there could be materials where the energy could be fed, right? You could have conductors or charges. The power would be delivered to those charges, and that is represented by E dot J. So this is the complete equation of continuity. It tells me that I have an electromagnetic energy in electromagnetic field. If that electromagnetic field is oscillating, the energy will go out. Then this electromagnetic field can see the matter, and it can pump energy into the matter, and that is given by E dot J minus term, because it feeds energy, it delivers power. And if there is a mechanism of getting energy, for example in case of plasmas in some cases, then this would be positive. E dot J would be negative, and that would mean that this term would be positive. Energy will be taken from it, will be like a source of energy. So remember our this analogy with the charge conservation. We said that we have a charge density, then there is a flow of the charge, then there could be charge sources. You have a similar thing. You have energy density, UVM, energy stored in electromagnetic field. It can change in time, but then if it changes in time, what can happen? The energy will flow out. That how much is flowing out is given by the Poynting vector, right? So divergence of the Poynting vector tells us how much energy is flowing out, and then it can energize material and feed some energy into some material. For example, you have energy that is coming from your antenna. Right there in the antenna, you have electromagnetic energy. It energizes the antenna and sends electromagnetic waves, and your mobile phones, they receive it, and the energy is fed to mobile phones. This is your term that takes care of your mobile phones. This is the energy that is fed to mobile phones. This takes care of the energy traveling from antenna to your mobile phones, and this is what you generate inside the antenna by changing electric and magnetic fields. And this is the equation of conservation of energy for electromagnetic field, and this we call as Poynting theorem. It is this whole equation is called as Poynting theorem. It tells us that how electromagnetic energy is transferred to the system and matter if electro and magnetic fields are changing in time, how the energy propagates in space. So I hope that this lecture I try to connect, because otherwise it's a very complicated thing if you go and just immerse into the derivations. And but it's a very interesting topic, because conservation of energy lies at the heart of physics. And there is one more principle called conservation of momentum. So in my next lecture, I will talk about conservation of momentum and Newton's third law in electrodynamics. It's a little bit interesting topic, and that would end our module 1. So we are done with some introductory course on electrodynamics, but it's kind of a kind of a freshman course. It's not a full-fledged course. So I will also be recording a full course on electrodynamics for master's students, but this was actually a freshman course, which is actually giving an idea of things and connecting you to the beautiful results of electromagnetism. So I hope you enjoyed the lecture the way I enjoy delivering them. Please ask questions, feel free. You can give some suggestions in comments, and do not forget to subscribe the channel. Thank you.